Hello listeners, in this video I will discuss crystallization of bicomponent magma. The outline of my discussion is, as you understand very well, you have studied unicomponent magma system and a separate video is devoted on unicomponent magma system. Now let us discuss about bicomponent system. Bicomponent magma system means which two components are called bicomponent magma system. Binary phase relations are mainly of three types: crystallization of two end members of a solid solution, eutectic crystallization of two mineral components, incongruent melting of a binary eutectics with peritectic reaction. Introduction. When two components are mixed together, three cases are possible in the nature. Mixed crystals form and are miscible. They form solid solution series of indefinite proportions. Miscible crystals of one and two components form by eutectic reaction and are of definite proportions. Two immiscible components form a crystal of intermediate composition by reaction only. Now, binary system with complete solid solution of two end members, I will take up this first. Minerals with similar lattice structures mixed together on atomic scale is called solid solution of one phase with the other phase. For example, olivine and plagioclase. When two isomorphous and miscible components in all proportions in solid state form homogeneous crystals called mixed crystals. Solid solution forms when both the components are isomorphous and constituent ions possess almost similar ionic radii and ionic charge. In such cases, both the components in solid and melt phases change during equilibrium crystallization and both the components mix completely with each other. Now let us have a phase diagram. Phase diagram, isobaric temperature composition phase diagram for albite and anorthosite, which is also abbreviated as ABAN system at atmospheric pressure. There are two important curves here. One is convex curve, which is liquidus curve, and our liquidus curve is everything is liquid or melt. And opposite to liquidus curve, you have a concave curve, which is called a solidus curve, and below this curve, everything is solid plagioclase crystal. And in between solidus and liquidus curve, there is a loop-like structure, and where you have plagioclase plus liquid both. The same thing I have shown here in color diagram. You can see here system with solid solution of two end members such as albite. The composition of albite is NaAlSi3O8, anorthite is CaL2SiO8, ABN where solid solution coupled with Na plus 1 and Si plus 4 substitution for Ca plus 2 plus Al 3 plus in constant Al2Si2O6 framework. Note the difference between the two types of fields. The blue fields are one phase field, that is liquid on the top and plagioclase on the bottom. Any point in these fields represents a line phase composition. The blank field is a two-phase field. Any point in this field represents a bulk composition composed of two phases at the edge of the fields and connected by a horizontal line. The same thing I have shown here for olivine system on where phosphorite and phthalate represented by Fo and Ma. Here Mg2SiO4 and Fe2SiO4 is there. The cation which is exchanged is Mg and Fe2 plus. Now let us discuss these two phases in terms of phase diagram. F equal to 2, phases F equal to 2, that is degree of freedom is 2. It must specify two independent intensive variables in order to completely determine the system, that is divariant system. Same as can vary to intensive variables independently without changing phi, the number of phases. In figure albeit, AB is on the right and anorthite on the left hand ends of the x-axis. These two systems behave like a isobaric one-component system. In this system, solid melt that coexist in a single phase at fixed temperature in equilibrium, that is P2. When applied in phase rule F equal to C minus P plus 2, it is expressed as F equal to 1 minus 2 plus 1, F, that is degree of freedom, equal to 0, that is invariant point. Pure albite and anorthite melts are at 1118 degree centigrade and 1153 degree centigrade at X and Y points respectively. When we add AB component to pure AN component, the melting point lowers down. In addition of pure anorthite or AN, melting point rises. Let's use phase rule for melt of intermediate composition. Consider a melt of composition A in figure at 1600 degrees centigrade. AN is 60 and AB is 40. Let it be bulk composition F. Bulk at 1600 degrees centigrade. Liquid composition is AN60 and liquid composition is equal to bulk composition as system entirely of liquid composition. Thus, in this case, P equal to 1, liquid, and C equal to 2. Application of phase rule F equal to C minus P plus 2, we have F 2 plus 1 minus 1 equal to 2. Let us see here this diagram again. F equal to 2 minus 2 plus 1 equal to 1, that is univariant. Must specify only one variable from among. The slope of the solidus and liquidus are of the expression of this relationship. It means that two-component liquid is at constant pressure, the F equal to 2. To define system, the variables are T, composition, that is X liquid anorthite plus X liquid albite. Further cooling to point B, AN60, AN40, in figure at 1475 degree centigrade, plagioclase forms is of composition C, that is AN content is 87 and initial crystal is AN rich. Line joining B and C of coexisting phases at temperature is called tie line. At any point on liquidus curve P equal to 2, coexisting liquid and solid and C equal to 2. So, F equal to 2 minus 2 plus 1 equal to 1. One variable is sufficient to define a system. On cooling, both liquid and solid vary composition. Liquid composition changes along liquidus line from B to G in figure, and plagioclase composition changes from C to H, indicate that both crystals and liquids become more sodic or albitic rich and denoted by liquid 1 plus plagioclase 1 equal to liquid 2 plus plagioclase 2. Such reactions have one F, that is 1 degree of freedom, and occur by exchange of components over a range of temperature and pressure called continuous reaction, forming a series of mixed crystals. Here is again I am showing you the diagram, a continuous reaction of the type liquid B plus solid C equal to liquid D plus solid F. Now we can explain this crystallization with the help of lever principle. The amount of liquid upon amount of solid equal to E upon dE, where dE equal to liquid composition, F equal to the solid composition, and E equal to the bulk composition, and it is shown with the help of lever rule here. Liquidus shown here with green and solidus is shown with the help of a blue color. Now lever rule. Let us understand what is a lever rule. Phase diagram gives an idea of modal proportions of phases and is done by lever rule. Fraction of liquid and solid phases for a given binary composition and T between liquidus and solidus line. Length of a tie line at any specific T, that means temperature, gives relative number of phases. Tie line in two phases regions equal to lever balance on fulcrum. This geometric approach is called lever rule. Let's consider the tie line DF in figure, and as per lever rule, liquid percentage equal to length of line, that is E minus F star 100 upon DF, whereas plagioclase equal to percentage equal to length of DE star 100 upon DF. Lever rule, amount of a given phase is proportion to the length of segment on opposite side of the bulk composition. Now lever rule continues here at 1445 degrees centigrade. EF equal to AN 82 and AN 60 is the composition, that is 22. DE equal to AN 60 minus AN 48, that is 12. Thus liquid percent equal to 22, 100 upon 82 minus 48 equal to 2200 upon 34 equal to 64.70 weight percentage. Solid percent 1200 upon 34 equal to 35.25 weight percent. In cooling continuous with a constant bulk composition, EF becomes larger, whereas DE becomes smaller. At 1340 degrees centigrade, corresponding solid composition of melt G, that is AN22, will be at H, which is equal to bulk composition AN60. On further cooling, tiny liquid of liquid AN22 is consumed. Here F equal to 2 minus 1 plus 1 equal to 2. What is the significance of this phase rule? And the lever explanation with the help of lever. The compositional zoning in plagioclase, feldspar or any mineral can be explained with the help of such types of phase rule. So when X plagioclase equal to H, then X plagioclase minus X bulk, and according to the lever principle, the amount of liquid equal to 0. Thus G is the composition of the last liquid to crystallize at 1340 degrees centigrade, bulk equal to 0.60. Final plagioclase to form is I point, when X plagioclase upon A equal to 0.60%. Now phi equal to 1, so F equal to 2 minus 1 plus 1 equal to 2. Note the following important inferences out of this kind of study. The melt crystallized over a T range of 135 degrees centigrade. The composition of solid changed from B to G. The composition of solid changed from C to H. Equilibrium melting is exactly the opposite. Heat AN60 and first melt is G at AN20 and at 1340 degrees centigrade. Continue heating, both melt and plagioclase change X, that means composition. Last plagioclase to melt is C, that is AN87 at 1475 degree centigrade. What is the significance? It explains the fractional crystallization and partial melting processes. Listeners, let us discuss about binary eutectic system. When two mineral components crystallize or melt simultaneously at a particular temperature, the temperature is called eutectic temperature and the process is called eutectic crystallization. Eutectic melting temperature and eutectic melting are reversed to it, and the eutectic crystallization is shown over here in this diagram. On abscissa, I have plotted diopside and anorthite. Diopside on my left hand side, anorthite on my right hand side, and temperature is shown with on the vertical axis. Cooling composition, A equal to bulk composition equal to AN70. Let us consider a point A in the graph, that is liquidous graph. On my right hand side, it starts crystallizing at 1553 degrees centigrade, and above this liquidous curve everything is liquid, and along this curve the first crystal starts crystallizing at 1553 degrees centigrade. It continues to crystallize, and let us consider a point A where the composition is AN 70%. Okay, then below that, cool temperature to 1455 degrees centigrade at point B. B point, the temperature is further lower down. The anorthite composition is different. Now cooling continues as X liquid varies along the liquidus. Continuous reaction, it's a continuous reaction. Liquid A reacts with the first crystal and anorthite plus liquid B is formed here. Now at temperature, further lowering temperature at 1274 degrees centigrade, phi equal to 3. So F equal to N2 minus 3 plus 1 equal to 0 invariant point. That point is invariant. P, T and composition of all phases is fixed. Must remain at 1274 degrees centigrade as a discontinuous reaction proceeds until a phase is lost. Discontinuous reaction all at a single temperature. Use geometry to determine. Let us see, left of the eutectic get a similar situation. Now note the following, the melt crystallizes over a T range up to about 280 degrees centigrade temperature. A sequence of minerals forms over this interval and the number of minerals increases as it drops. The minerals that crystallize depend upon temperature. The sequence changes with the bulk composition. Now, let us explain the texture which are found in igneous rocks with the help of this eutectic crystallization. Agate forms before crystallize. Agate is shown over here in this photomicrograph with the help of high second order, third order polarization colors, and it is surrounded by plagioclase, which is showing the gray color with repeated twinning, and these plagioclase forms before crystallization of agate, and it gives rise to ophitic texture. In ophitic texture, you have a big crystal of clinopyroxene, and in this clinopyroxene, there are small laths of plagioclase. They are embedded within the clinopyroxene crystals. This forms the right side of the eutectic crystallization. Last melt to crystallize in any eutectic mixture is the eutectic composition. Equilibrium melting is the opposite of the equilibrium crystallization. Thus, the first melt of any mixture of diopside and anorthite must be the eutectic composition as well. Fractional crystallization can also be explained with the help of these diopside anorthite two-component magma system. The isobaric temperature X phase diagram at atmospheric pressure, it can explain the fractional crystallization. The partial melting can also be explained with the help of such types of phase diagrams. Now, viewers, let us summarize what we have studied or what we have discussed in this video. We have discussed two phases. They coexist only at phase boundary. There are three cases. Number 1A, mixed crystal form which are miscible, that is solid solution. And B, mixed crystals of 1 and 2 compositions miscible in a fixed ratio form due to eutectic reaction. And C, two miscible components form a crystal of intermediate composition. Lever rule. Let us summarize what is lever rule. To determine fraction of liquid and solid phases, we use lever rules. Binary eutectic system, a new melting point is called eutectic point. Temperature at which eutectic melting occurs is called eutectic temperature. Thank you, viewers.